In this section, we're going to look at our last type of differential equation, which is going to be a linear differential equation. And so we're going to define what a linear differential equation is, and we're going to find a formula to be able to solve those linear differential equations. And then we're going to be able to actually solve them and then also solve the initial value problems associated with those. And so how does a linear differential equation differ from a separable or one where the derivative is just on the left-hand side, which is technically separable anyway? So this is our form for linear. dy dx is plus some p of xy is equal to q of x. Okay, so if you can write a differential in that form, that's a linear differential equation. We're first going to multiply, and this is just to derive the formula that we're going to use throughout for a linear differential. We're first going to multiply by this integration factor, okay? And somebody really smart came up with the integration factor, so you don't necessarily have to worry about where it came from, just worry about that it works. So we're going to multiply all three terms in this linear differential by this e to the p of x, or e to the integral of p of x dx. And so you might be thinking, well, why would I want to do that? Well, what that does in this particular example is that it makes it so that these two terms actually become a product rule of derivatives. All right, so if we think of f as y and we think of g as e to the integral of p of x dx, then we could use our product rule. So f prime would be dy dx, right? And then g prime, using the chain rule, would be the integral of e is e, so e to the p of x dx, but then we would multiply by the derivative of integral p of x dx. But we know that the derivative of an integral just cancels each other out. All right, so we would just be left with p of x. All right, and so you can see that this is going to be right here. This is going to be like g prime, and this is going to be f. All right, and this is going to be like f prime, and this is going to be g. All right, so it does follow a product rule. And so what we're going to do is we're just going to go backwards from that product rule. And that's how we get like this dx, y e to the integral of p of x dx times the q of x e to the integral p of x dx. All right, so that's just reverse implicit differentiation, or reverse product rule, if you would. Now we're going to integrate both sides, and we know when we integrate a derivative, they cancel each other out. And so we're left with just this y equals integral of p of x dx. And then when we integrate this animal, we have our constant of integration plus c. And then finally, if we were to divide just by this e to the integral of p of x dx, then this would be our formula. Okay, now when I do these problems, what I'm going to do is take it a step further, and I'm going to define I to be e to the integral of p of x dx. And so what we could do is we could actually rewrite the former as y equals 1 over I times the quantity of the integral of q of x times I dx plus c. Right? So this might be a little bit easier to swallow than something as ugly as this. All right, they're both the same thing. This is just putting this intermediary step in. All right, so let's take a look at an example at work of being able to use this formula that we just found. All right, so we have a really basic linear differential. Y prime minus 5y equals 15. Y at 1 is equal to 6. Find a general, find a particular, and then similar to what we did in the very first problem in the previous section, we're going to plot the direction field, and then we're also going to plot the particular solution. And this is a way to verify our answers. All right, so in this example, y prime at t minus 5y equals 15 is already in the form of a linear differential. Now notice that our variables are in terms of t, okay, instead of x. So we're just going to change all the x's to t's. All right, so in this case, p of t is going to be equal to -5 because it's the coefficient of the y, and then q at t, or q of t, is going to be 15. When we start to solve these, the first thing we're going to do is we're going to find the integration factor. Right? So first step, we're going to find I, which is going to be e to the integral of p of t dt in this case, which is going to be e to the integral of -5 dt, which is going to be e to the minus 5t. All right, so that's pretty easy to be able to find the integration factor for I. Right? Now, next thing we're going to do at this point is we're going to substitute it back into this formula. And again, we're going to replace x's with t's because our independent variable is t. So y is going to be equal to 1 over I, which we just found to be e to the minus 5t, times the quantity of the integral of q at t. Okay, so just substituting there, which is 15, times I, which is going to be e to the minus 5t. We have our dt, and then a plus c. Now we just integrate this. Okay, so step 3, we integrate. So y is going to be equal to 1 over e to the minus 5t. When we integrate this, we are going to go from the reverse chain rule. So we're going to divide by -5. So this is going to be 15e to the minus 5t over minus 5 plus c. We could distribute this e to the minus 5t, and notice it'll cancel out these two factors, but the c will still have it in the denominator. So one way to write the general solution to this would be y equals -3, since 15 over -5 is -3. This and this cancel each other out, plus c over e to the minus 5t. But of course, if we divide by e to the minus 5t, that's the same thing as just c e to the 5t. All right, so another way to write this is ce to the 5t minus 3. All right, so this is our general solution. And that helps us solve letter A. Letter B, for part B, we have y at 1 equals 6. So that means when t equals 1, y is 6. So let's substitute. So we're going to get 6 is equal to ce to the 5 times 1 minus 3. We're going to add 3 to both sides. So 2 equals ce to the 5th. And then finally, we're going to divide by 5, or e to the 5th, excuse me. So 2 over e to the 5th is equal to c. And then we can just substitute immediately back in here. So we get that y is equal to 2 over e to the 5th, e to the 5t minus 3. All right, and that's certainly a fine solution. There's nothing wrong with that. Another way to write this, okay, is to say that y equals 2 e to the minus 5th, e to the 5t minus 3. And notice that these have a common base, so you could add the exponents. So another way to write this would be 2e to the 5t minus 5 minus 3. All right, and that might be the most simplistic way to write this. All right, so just be cognizant of your algebra rules when you guys are trying to solve these types of problems. Sometimes you have to simplify it a little bit more than just to give an answer. All right, now, part C, we are going to plot the direction field, okay, or the slope field for this. And so all we're going to do is just solve it for y prime by adding 5y to both sides, okay? So for part C, remember our original differential was y prime at t minus 5y is equal to 15. So we're just going to add 5y. So we get y prime at t is going to be 15 plus 5y. And this is what we're going to put in Desmos, okay, along with this as well. All right, so if we flip over to Desmos, all right, and we're just going to type in the slope field, which was 15 plus 5y. Right, so there we go. And this was an old one that we had from a previous example. So not all that interesting of a slope field. All right. And recall that our solution was going to be 2e to the 5t minus 5 minus 3. All right. So if we substitute that back in, so we have 2exp 5t minus 5 minus 3. All right. And there we go. And this is perfect, right? Because it kind of falls right onto this this equilibrium point, and then all of a sudden it just kind of upturns. Okay, we can kind of see that happens like right about here, and it's just following the slopes. All right, so it fits perfectly into the slope field. And again, that's the whole purpose of plotting the slope field, is to be able to see whether or not your solution looks like it's correct. All right. It doesn't mean that it is, but at least there's evidence to suggest that it is. Okay. All right. So for the rest of this video, all we're going to do is we're just going to employ these methods to be able to solve these sorts of linear differentials. And remember, there are 3 steps. First, we solve for I, then we plug it into our formula, and then finally we just integrate whatever that leftover integral is inside. And then we might have to do a little simplification for this.